At this point, you've watched several videos that have pointed out our misconceptions about the way horizontally fired projectiles behave. We've also seen how these stroboscopic pictures are taken and overlain on each other so we can observe the motion. In this screencast, we're going to detail looking at projectile motion in 2 dimensions when projectiles are fired horizontally, only horizontally. So the first thing we want to look at is the behavior of these 2D projectiles. The first thing you've already seen from the videos and the examples is that even though one projectile is fired with a horizontal velocity and one is merely dropped, they both hit the ground at the same time. So in the stroboscopic picture, with the stroboscope being shown, at equal increments, pictures are taken of both balls. And then each of those pictures is superimposed on the last to produce this image. So if we look backward, we can see these two here, these two here, these two, these two, these two, these two, these two, these two, this pair, and this pair, and this pair. So that's time 0, that's time increment 1. Now this second ball here is difficult to see because of the launch apparatus. Each of these horizontal lines is exactly the same height. So we can see that with each time increment as it moves down, they are at the same height always. Counterintuitive. This is a picture that one should probably burn into one's brain when it comes to these horizontal pictures, horizontal projectiles being launched. So you may wonder, why is it? Our misconceptions told us that something else would happen. So why does this actually occur? And the answer is forces. Let us suppose before release that the projectile being fired is, let's say it's a bullet, and we have the barrel of a gun, like so. Now we'll study forces in more depth later. But the answer to why this occurs is forces. And that is because acceleration is caused by unbalanced forces. So if there's acceleration, then there are unbalanced forces. And this is a reversible statement. If there are unbalanced forces, then there is acceleration. To switch that around, if we were to say the forces are balanced, then there's no acceleration. And if there's no acceleration, then the forces are balanced. So 2 statements, and they are reversible with each other. So let's examine the forces we have here on this particular projectile. Let's say it's a bullet. Now the first thing we have acting on it is we have gravity acting downward on this. So we have a force of gravity acting downward on it. But the bottom of the barrel is holding the ball up. It's exerting a force upwards. And that force is called the normal force. So if you notice, this force and this force are equal to each other. They're balanced. And since they're balanced, there's no acceleration. This thing is not accelerating up or downward. It's balanced. Similarly, if I'm looking at this and I know that it's not accelerating up or down, then I know the forces acting on it must be balanced. But there are also a whole host of gas molecules inside here, like this, that are expanding. This leads to an applied force. An applied force on the bullet. So you can see these two are balanced, but there's no force resisting this applied force. Now you might be thinking there's air resistance, but at low speeds it's negligible, and the projectile is usually pointed. So we generally consider, in this case of the projectile, the air resistance to be very small. And of course, since it is accelerating out here, we know the applied force wins. So these two cancel each other, and this is the only force acting on it, so it's only accelerating in this direction. Now, at a few moments later, after the release, after it's left the gun, like so, we can examine the forces acting on it. And when we examine those forces, of course, gravity is acting on it. But the barrel is not at the bottom pushing upward, so there is no normal force. And the gases now are expanding. The expansion is almost all complete, and it has left the barrel, so now it's exerting this force on the air here and not on the projectile. So the only force acting on this is gravity. The only force is gravity. So what that means is that this gravity force is unbalanced. That means it will accelerate. Vertically, it accelerates. But if you notice horizontally, there are no forces. None at all. So those forces, this non-force and this non-force, are balanced. So if it's a balanced force, then there is no acceleration. Horizontally, no acceleration. In other words, it travels at constant velocity. This is why, and this is fundamentally important, the next thing we want to consider is our frame of reference when looking at these, considering projectiles. So our first frame of reference we're going to consider is what I call the omniscient frame of reference. Usually you only come across this term in English class because the person is all-knowing or all-seeing. In this frame of reference, looking at the projectile, you can see that, and just I'll draw in like the gun, or if it's a cliff or a table, we have a ball rolling in this direction, and this is the edge of the cliff. And I'll highlight it in orange, the edge of the cliff or the edge of the table. We roll the ball along the edge of the table, and then what happens? Well, it has some initial horizontal velocity, just like the gun did. And of course, when it's on the table, we have the force of gravity, we have the force normal canceling each other. They're balanced, so there's no acceleration upward or downward. But once we leave the table, there's no longer a force upward and we only have gravity, so it will tend to accelerate. But it already has this initial motion. The law of inertia says that an object in motion will tend to stay in motion. In motion tends to stay in motion. At rest tends to stay at rest. Unless there is an unbalanced force, which we just spoke about on the previous slide. So this projectile has inertia. And once it gets to this point here, it's going to preserve its state of motion, except because of the imbalanced force. So it's going to travel in a constant speed horizontally, and it's going to accelerate vertical. Why? Because there is an unbalanced force vertically and balanced forces horizontally. So our frame of reference here is we can see that the projectile will take the red path. We will observe a red path. We roll this thing off the table, and it will take this parabolic curved path. We will see the truth from our frame of reference. But this truth that we see from this frame of reference is built upon vertical motion that's accelerating and horizontal motion that is constant, as a constant speed, a constant velocity. So this resulting parabola is this motion in the x plus this motion in the y. Produces this two-dimensional motion like this. And we get to see the truth of it from this particular omniscient frame of reference. Now let's look at each one in isolation. So let's consider frame of reference 2. Frame of reference 2 is the vertical. So now what we have here in this setup is we have about a 2-meter height, and we have Spider-Man over here, who's a little bit less than 2 meters tall on this wall. And he is located 50 meters away. Now, I couldn't draw it to scale, but 50 meters is very, very far compared to this 2 meters. In fact, it's 25 times further. So it's very, very, very far away in comparison to this vertical change. That's important. That's critical. You will also notice that his line of sight is perpendicular to the direction of motion. The motion is vertically, and he is looking horizontally. So he's very far away and perpendicular to the motion. And what he observes, even though the thing is taking this red path, is it looks to him as if it is just simply falling. Why is that? Well, that occurs because he's very far away. How we usually detect something coming toward us is either we infer it based on some behavior of a person. So if we see a person walking down a hallway toward us, we see their feet moving and we see their arms moving, which leads us to draw the conclusion that they're coming toward us. We also, though, if we could only see them from the neck up, might conclude that they're coming toward us because their head will appear to get bigger. Their head will appear to get bigger. Let's suppose we were to get closer to Spider-Man. You will see that Spider-Man's head gets larger. And we call this the angular magnification. So when something is moving close to us and a significant part of the distance is covered, it will appear to grow larger. It will appear to grow larger. Now, as Spider-Man looks at this is only 2 meters, and even though the projectile is coming towards Spider-Man, the amount it's coming towards Spider-Man is very small compared to the total distance. In other words, he is not going to see the projectile of the ball get larger. Because the amount of this 50 meters is very small, he won't see it get larger. Imagine you're at school looking down at the end of the hallway and you see the size of someone's head. They come forward 3 steps. Their head will not appear larger. They've covered a very small portion of the distance, so their angular magnification, their angular size, will not change. So even though the object is coming closer, the change is so small compared to the total that he will not observe it. So from this frame of reference, very far away, looking at the vertical, Spider-Man will see only the vertical motion. If you ask him what's happening, he's like, oh, the ball just drops. That's what he would conclude. Let us now consider the third frame of reference. The third frame of reference is way above this whole thing. So let's suppose now we are in a helicopter 50 meters above this ball that's rolling off the edge of the table. Again, this distance is very large and I can't draw it to scale. This distance here represents only about 1 meter. So again, very, very small distance. And we know this height, the vertical drop is only about 2 meters. So even though we know from our frame of reference that the ball is doing this, the red path, the change in height is so small that someone in the helicopter at a long distance will not see the ball change its size. So all people in the helicopter will see is the green dots, constant speed. If you ask them, they'll say, oh, the ball's just moving forward at a constant speed. They will not be able to detect that it's moving downward. So again, from this perspective, the key elements are that the person, the helicopter, is very far above, and the observation, if you look at the line of sight, is vertical when the motion is horizontal. In other words, the view of it, the perspective, is perpendicular to the motion. That's how we see the true nature of it. So again, why is it the people in the helicopter would say that it's moving at constant speed? Because they will not see the ball get smaller, even though in fact we know it's moving away from them. Because the change is so small, only 2 meters compared to the 50, they will not see it change size. Just like that friend way down at the other end of the hallway, just by taking 3 steps forward, we won't see the size of their head change. So this is really important because we know how to study each of these types of motion. We know how to study horizontal constant motion, and we know how to study vertical accelerated motion. But this two-dimensional motion is much more difficult to study. So we treat each one separately because they don't interact with each other. It also leads to a kind of a paradox. If we, in the omniscient point of view, frame of reference 1, are talking to Spider-Man on the phone, and we're on a conference call with people in the helicopter, there ought to be some things that we all agree about. And that is when the ball is released and when the ball stops. We should all agree on the amount of time it takes for that thing to occur. So that time should be the same. I would draw your attention that Spider-Man, who's going to be over here, Spider-Man observes this blue dot. And then this one, and this one, and this one. Now we're observing the red because we have the omniscient point of view, but Spider-Man's viewing the blue. The people in the helicopter are viewing the green. And notice, in this case, we viewing the red, Spider-Man viewing the blue, and the helicopter viewing the green will all agree about this time that the ball is here. Spider-Man will say, yeah, it took a certain amount of time to fall from here to here. The people in the helicopter will say, yes, I agree, it took the same amount of time to go from here to here. And we will agree that it took the same amount of time to go from here to here. So we will all agree on the time, but we will disagree about just about everything else. Spider-Man will say it's accelerating. The people in the helicopter will say it's traveling at constant speed. And we will say, well, it's actually taking a parabolic path in 2 dimensions. So our frame of reference, even though we're all observing factually the same thing, we'll see something different based on our point of view, our frame of reference. So you may wonder now, how do we solve problems and answer questions about this? Well, let's take a look at a problem like this. We've got a ball rolled horizontally at a speed of 3 meters per second from the edge of a 100-meter cliff. When will it hit the ground? How far from the base will it land? And what will its impact velocity be? Let us first deal with the vertical. Vertical motion is Spider-Man. That's the blue. Our first challenge is to set up a frame of reference. Do we make the top 0 or the bottom 0? Probably simplest to make the top 0. So we're going to select this one for our vertical. We'll start with our generic equation for velocity. V equals AT plus V0. The acceleration that it undergoes is due to gravity. So that velocity is negative 9.81 times the time, and vertically the initial velocity is 0. It wasn't thrown upward, it wasn't thrown downward, it was just dropped. It was as if it were dropped. And that's how Spider-Man would describe it. So we're left with this as the model of our velocity. We start at time 0 vertically. Vertically, the initial velocity, Spider-Man will say, is 0. And we can see that the direction is downward, like so. And again, on a velocity time graph, what we can read is the velocity time. The gradient is the acceleration. And notice it's negative, and it's constant, caused by gravity, negative 9.81. And the area will give us the displacement. And if you recall, the area here will be negative, which means the displacement will be negative. In our coordinate system, the displacement would be negative. Now it's time to consider the position. We have y and t. Now if we make this particular location 0, we know the initial position is 0. We start with our generic equation, y equals 1/2 a t squared plus v0t plus y0. Now in the vertical direction, it is accelerating. So we have negative 9.81 because the acceleration is caused by gravity. And as we said before, the initial velocity in the y direction is 0. It's as if it were dropped. So this term drops out, and we said the initial position is 0 because we set this location equal to 0. We chose this reference frame. So now we have a model of y equals negative 4.905 t squared. That's the model that describes our y. So can we determine when it hits the ground? Well, what do we know when it hits the ground? The cliff is 100 meters tall, so we know it will hit the ground when it reaches a position of minus 100. So minus 100 equals negative 4.905 t squared. And then t squared is minus 100 over negative 4.905. Which gives us t squared equal to 20.387, and then t is equal to the square root of that. Which is 4.51524 seconds. Now we had three significant, 100, we have 100 up here, which is, with that period there tells us that all three are significant, and this has three significant digits, and we use 9.81, which has three significant digits, so we'd report three significant digits, so time is 4.52 seconds. So what would the velocity be? Vy, velocity in the y direction, is now going to be equal to negative 9.81 times the time, which is 4.51524. So Vy is 44.29447 meters per second. And again, we have three significant digits, so Vy is going to be 44.3 meters per second. Boxed answer. Boxed answer. So in other words, we just did y. Spider-Man says it's going to take 4.52 seconds, and its impact velocity, if you were able to measure it, would be 44.3 meters per second. He sees it moving downward. He sees it moving downward at 44.3. So one last thing we need to do here is our graph of position. Our position started at 0. And we have a model of negative 4.905 t squared. Now this is a parabola. It's negative, so it's downward cupped. But what we know is it starts out slowly. So in the first second, it covers a certain distance. And the next second, it covers more and more and more and more. And that's what produces the curve. So this is the equation of a parabola, and there is the equation for y. Now it's time to consider the horizontal, now that we've resolved the vertical. So now we're taking the point of view, or the frame of reference of the helicopter. When we examine the reference frame we need to set up, it makes sense that we were starting in this position so that this would be 0 where we started. So this would be 0, this would be our positive direction and our negative direction. Let's first consider the velocity time. And so we start with our generic equation, v equals at plus v0. And so then we put in the acceleration, and we look at the green dots, and we recall that there's no acceleration. It's constant velocity. So the acceleration is 0, which means this term drops out, and so the velocity just equals v0. And that velocity was 3.00. There is no model per se. So what we have for a graph is simply this. A velocity of 3 in the horizontal direction that doesn't change. Well, let's see if this makes sense. What can we read from a VT graph? Velocity and time. What does the gradient tell us? It tells us the acceleration. Now the gradient in this case, the slope, is 0. The acceleration then is 0. It makes sense. And the area, of course, tells us the displacement. Notice this is a positive velocity, so we're going to be getting positive displacements. Let's see if that makes sense. 0, yes, the displacements will be positive from that 0. So it all makes sense. Next, let us consider the position in the x direction. So now we're going to have the x position versus time, and we start out with our generic equation, y equals 1/2 at squared plus v0t plus xo. It's supposed to be x, so we're dealing with the horizontal x. So let's see, x equals, well, the acceleration is 0. So this term drops out. The initial velocity is positive 3, so we have 3t, and the initial position is, in our reference frame, 0. So this is our model here, x equals 3t. Velocity of 3 meters per second. Oh, so this gets very easy in the x direction when the motion is constant. So all we need to know is the time, which we found on the previous page. On the previous page, we found that the time was 4.51523641 unrounded. And I stored that in my calculator so I can use it later. And we get 13.54570923 meters. Now the velocity was 3.00 with 3 significant digits. Time we had was reported with 3 significant digits. Everything was based on 3 significant digits. So there's our 3. The 4 is smaller, so we have a position of 13.5 meters. Boxed answer. Now for the people in the helicopter, they're going to say it moved 13.5 meters. And the people in the helicopter are going to say it's traveling at 3 meters per second. Now, if we remember on the previous, so this is Vx, and this is x. For Spider-Man, y was minus 100 meters. So they disagree on the position. And when we look at Vy we had as negative 44.3 meters per second. So there's disagreement. And we discussed this previously, that if we were all on a conference call, the two perspectives, the helicopter and Spider-Man, and us with our omniscient view would see something very different. So this is the helicopter, this is Spider-Man, this is the helicopter, excuse me, this is Spider-Man, and this is the helicopter. So Spider-Man is going to say, it didn't move at all. It didn't come close to me. There was no movement in the x direction. People in the helicopter are going to say, no, it came closer to you by 13.5 meters. So they're going to disagree about the movement. And they're going to disagree about the velocities. And so will we. Each of us, the helicopter above, Spider-Man from the side, and us with our omniscient view, seeing the true two dimensions of the motion, will disagree on everything except the time, the speed, and so forth. So we don't agree with either of them. We don't agree with either of them, except to say, yeah, we'll agree that the parabola, in the x direction, it did land 13.5 from the base. And yes, it did fall 100 vertically. We will agree with that. But we'll say the path it took was certainly not either of those numbers. In fact, we might even say it's the hypotenuse of this. We could then see that we would say that in the x direction it was 13.5 meters, and in the vertical direction it was minus 100 meters. But we say that the actual displacement or change in position is this. So the helicopter says this is the displacement, Spider-Man says this is the displacement, and we say no, this is the displacement. And in reality, we have the truth. And of course, these two are perpendicular to each other, so we can use the Pythagorean theorem to solve the actual displacement, delta x. And let us do that. So we have a squared plus b squared equals c squared. 13.5 squared plus 100 squared equals c squared. And then c is the square root of that whole mess. Underneath the radical, it's 10,183.4. And then c is 100.91 meters. So then c, to 3 significant digits, would be 101 meters. So, when asked what's the displacement, helicopter will say 13.5 meters. Spider-Man will say no, it's 100 meters. And we will say, well, from our omniscient perspective, the displacement was actually 101 meters. We take this quantity, the change in position, this displacement, this vector, and this vector, and we draw the second vector at the end, and the result, we call this the resultant, is from the very beginning to the very end. So the true displacement is 101 meters. And of course, for it to be a vector, we need to describe the direction, which would be that angle. And that angle, we could call this the opposite side, and this the adjacent side. And we know that the tangent of that angle theta is the opposite, 100, over 13.5. So then theta, the angle, is equal to the inverse tangent of 100 over 13.5. So theta is 82 degrees. So what we would say about the displacement delta x is 101 meters at this angle here, 82.3, it was actually a 0.3 degrees, 82.3 degrees south of east. This direction being east, this direction being south, and we'd swing the angle this way, so we're going south from east. Delta x, the displacement, is a vector, so it needs a magnitude, 101, and a direction, 82.3 degrees south of east. So that's its actual displacement. Now I just want to jump back here. We forgot to graph this. In the x direction, we started at a position of 0. And the equation was x equals 3t. In each interval time, it's traveling at a constant speed, like so. What can we read off this graph? Position and time. What does the gradient or slope equal? It's delta x over delta t, which is the velocity. And the area tells us nothing of significant. Notice the velocity remained constant at 3, so we have a straight line. It's all consistent. So if we go back to our original questions we were asked, have we answered them all? When will it hit the ground? Yes, we know it's going to hit in 4.52 seconds. We found that out very quickly. And that's always going to come from studying the y direction first. How far from the base it will land? Well, how far from the base it will land has to do with the x. And so when we solve for the time vertically and plug it in here, we find it lands 13.5 meters from the base. What will its impact velocity be? Well, if you're talking to the helicopter, it's going to say it was traveling at 3 meters per second when it stopped. Spider-Man's going to say he was traveling at negative 44.3 when it was at impact. But it turns out, from our perspective, the omniscient perspective, that is again not true. Neither one is totally correct. So let us consider. We have in the horizontal 3 meters per second. And vertically, we have 44.3 meters per second. You can see that when it's traveling in this parabolic path, it's getting some additional speed because of the horizontal, in addition to just the vertical. So we expect it to be more than 44. And it's the contribution that this 3 makes. Well, if I have 3 and I add 44.3 to it, the resultant I get, the velocity, the resultant is going to be the sum of this velocity and this velocity. This is a right angle, and we can solve for that velocity. A squared plus b squared equals c squared. C is going to equal the square root of a squared plus b squared, and c is then going to be the square root of 3 squared plus 44 point, and the unrounded value 2947 squared. And that gives us 44.396 meters per second. Now we have 3 significant digits, so that means that C would have to be 44.4. The 9 causes the 3 to round up, meters per second. So we know the magnitude of this is 44.4. Not much, but we can see it's 1/10 of a meters per second more. So really what drove the impact velocity was mostly the falling, not the horizontal. It was predominated by the vertical. So of course, if we're looking for the impact velocity, well, we have a magnitude now of 44. We have a velocity that is equal to 44.4 meters per second, but we also need, since it's a velocity, a magnitude, and we need the direction. So the direction, again, we can use tangent of this angle, and we have tangent of theta is 44.3 over 3. Theta is the inverse tangent of 44.3 over 3, and theta is and theta is 86.13 degrees. 0.13 degrees, which would be 86.1 degrees. Now you'll notice that these two angles are different. The displacement angle is 82.3, and the velocity is at 86.1. You might think at first that they should agree with each other, but they actually should not agree with each other. And here is why. If we go back to our picture here, and we look at the trajectory of the projectile, what we should see is, and acknowledge, is that the velocity is tangent to that curve. So in other words, at this particular instant in time, what is the direction it's traveling? Is that direction. But if we look at the displacement, like so, the direction is this. So you can see they're not actually in the same direction, and in fact the velocity should be a steeper angle than the displacement angle. Something that's not intuitively obvious. So now how would we use this, the average velocity table, to solve a problem like this? Well, we would need to break it down vertically and horizontally. So let's do the vertical thing first. At time 0, we have a velocity of, in the vertical direction, 0, then minus 10, minus 20, minus 30, minus 40, minus 50. Now we happen to know a priori that it impacts between 4 and 5 seconds. That's fine. Average speed, irrelevant at that point. Average speed here is minus 5, minus 10, minus 15, minus 20. 0 plus negative 50 is negative 50. the average of those two numbers is negative 50 divided by 2, or negative 25. Remember, displacement is always equal to the average velocity multiplied by the time. So the displacement vertically is 0 at time 0, hasn't fallen at all. Negative 5 times 1 is minus 5, minus 20, minus 45, minus 80, minus 125. So clearly from the table we could predict that impact would occur somewhere between 4 and 5 seconds. We might even say, we could do a linear approximation, say, oh yeah, halfway between these two. Where's 100? 100 is 20 down and 25 up, so it's maybe about halfway, but the second half is traveling faster. But even if we said it was then maybe 4.5, that gets us closer than saying it's 4 or 5. Now let's take a look at the horizontal. In the horizontal, there's no acceleration. We just know that distance is always equal to the average velocity times the time. Horizontally, the velocity was constant, a constant 3. And if we know the time estimated from the table is 4.5, well, that gives us 13.5 meters. So the horizontal distance would be 13.5 meters. Now, ironically, or not so ironically, when we come back to our perfectly analytical complex calculation, it's 13.54. And we ended up with an answer of 13.5. Now, the table method will not always get us so close, but this is how we would use the table method to solve this kind of